Welcome to the Deep Dive. Today we're tackling a really fundamental concept, the equation of a line.
That's right.
Think of it like learning the basic language, for describing straight relationships you see everywhere. We've gathered some great material that really breaks down how these equations and the lines we see on a graph are connected.
Yeah, they lay out the groundwork pretty clearly. We're talking linear equations, how they look visually as straight lines.
So for you listening, if you enjoy grasping new ideas efficiently, this deep dive should give you a really solid handle on how it all works.
Exactly. We'll pull out the main ideas, look at some, practical examples. The goal is you walk away with clear, usable knowledge. It's essential stuff.
Okay, let's dive in then. This fundamental language. What is a linear equation, really, at its heart? And how does it connect so directly to a straight line?
Well, okay, at its core, a linear equation is just one where the variables, usually x and y, they only show up to the first power.
So no 6(2)(2) or 63(3) or anything complicated like that?
No, none of that. Just simple first power. You'll see them like 3 by 20y equals 7.
Or maybe 6x plus 5y equal 8 of 8.
Perfect. Or even simpler ones, like just 6 equals 5, or y plus 3 equals $7. Those count too.
Okay.
And the really cool thing, the connection is this. Every single linear equation you write down, it draws a perfectly straight line on a graph.
Every single one.
Every single one. And, flip side, any straight line you can possibly draw on a graph.
It has a linear equation.
It can be described perfectly by one. It's like a direct translation between the algebra and the picture, the geometry.
So it's genuinely a two-way street then?
Absolutely. Which leads to a couple of key ideas, really.
Yeah.
First, if you've got a point, say, coordinates 6y, that point satisfies the equation of a line if and only if.
If it actually sits on a line when you draw it.
Precisely. It's got to be on the line visually for its coordinates to work in the equation algebraically, like a membership test.
I like that. A membership test for points wanting to join the line club.
Exactly. And the reverse is just as vital. Any point a line passes through will satisfy that line's unique equation. Always.
Okay, and our sources give examples of this, right? Like checking if a point is on a line.
Yeah, they do. For instance, is the point $4 on the line, $3 is 10 allowance, plus 5y equals 2.
So we just plug in, settle $4 and sue otherwise $2.
So $3 plus $5, which equals 2.
It matches. So yes, it's on the line.
It is. But then they try another one, $204 at the line, 6 pi 4 was plus 8, which plus 8 too.
Okay, so $2, $3, 4 plus 8, that's $2. 12 plus 8 was, which is -2?
Right, -2, not 0. So that point is definitely not on that line.
Simple check, but really shows that connection you mentioned.
It does. And they have another neat example, finding an unknown. Like if you know a point dollars is on the line 3 by 8y equals 2.
So you plug in the unknown k for sexly.
3k 8 to 2, so 3k 16 is 2.
Add 16 to both sides. $3 equals 18, so tellers must be 60.
See? You can use the relationship to find missing pieces.
Now, here's a slightly trickier one from the sources. Does the line $3 x equals y plus $1 cut a line segment? The one joining A, $2, $3, and B, $4 a baller, exactly in half. How do we use the equation for that?
Okay. Well, the key here is the midpoint. If that line bisects the segment AB, it must pass through the exact middle of AB.
Right, the midpoint. And we have a formula for that. Average the x's, average the y's.
That's the one. So $4 plus 4, 2 plus 1, 2 plus.
Which gives us fractal, or $1, that's the midpoint.
Okay, so $1 is the midpoint. Now, does this point lie on the line $3 y plus $1? We just test it, like before.
Plug in tax $3 and $1 or 2. So does $3 equal $2 plus $1?
Well, $3 is more as a $3. Yes, it does.
So the midpoint is on the line, which means the line does bisect the segment.
Exactly. It's a neat application of that core principle.
Okay, points on lines, checking coordinates, got it. Now let's talk about what gives a line its sort of personality. Its direction and steepness. Inclination and slope come up next.
Right. So inclination, think of it as the angle. It's the angle a line makes with the positive part of the x-axis.
Okay, the part going to the right.
Yes. And crucially, it's measured above the x-axis, usually counterclockwise. That gives a positive angle.
Counterclockwise from the positive x-axis. So a line going up to the right would have a positive inclination.
A positive inclination, yeah, between 0 and 180 degrees usually.
Yep.
Think of it like the direction a ramp points.
Okay. What about just the flat x-axis itself?
Well, that's flat, so its inclination is $0. Same for any line parallel to it.
And a vertical line like the y-axis?
Straight up and down. That's an inclination of $90. Same for any line parallel to the y-axis.
Okay, inclination is the angle. How does slope relate to that?
Slope is where we quantify the steepness. It's often called m. Mathematically, slope is the tangent of that inclination angle. 1 meter tan theta.
Ah, tangent from trig. So slope is more nit or tan theta.
Exactly. It connects algebra, geometry, and trig. Think of slope as rise over run, how much the line goes up vertically for every unit it moves horizontally.
So a steeper line would have a bigger rise for the same run, a bigger slope.
A bigger slope, yes. And it's more than just steepness. It often represents a rate of change in real-world stuff, like speed or growth rate, if the relationship is linear.
That makes sense. So what's the slope of the x-axis then? Inclination, zero load?
Slope is tan zirc, which is just zero law. Makes sense, right? No steepness.
Yeah, totally flat.
Uh-huh.
And the y-axis, inclination, 90 zerks.
$90, that's undefined. You can't divide by zero in the rise-run sense because there's no run for a vertical line.
Ah, okay.
Yeah.
Undefined slope for vertical lines. Got it. And the sign of the slope tells us something too.
It does. Positive slope means the line goes uphill, left to right. That corresponds to an acute angle of inclination, less than 90 degrees.
And negative slope.
Means the line goes downhill, left to right. That's an obtuse inclination angle between 90 and 180 degrees.
The sources had examples like inclination $45.
Right. Pretend $45 is exactly 1. So slope $900 letter, rise equals run.
And inclination $135. That's obtuse. Or maybe 45 sector clockwise.
Both give the same slope. Tan 135 circ is also -1, so $100 one netter. It goes down 1 unit for every 1 unit across.
Okay, cool. Now, what if we don't know the angle, the inclination, but we just have 2 points the line goes through? How do we find the slope then?
That's probably the most common way you'll calculate it. There's a formula. If you have 2 points, say P epsilon 1, Y, and Q, X, Y, Y, 2, Y.
Right, I remember this one. It's the difference in the y coordinates divided by the difference in the x coordinates.
Exactly. 1 negates say Y1. You can also do xi1 negates 2y1. You can also do frax phi y1 dex y1 too. Just make sure you subtract in the same order top and bottom.
Is the rise nigh difference over the run
You're
second
good.
difference?
And there's an example line through A2 $3 and B2 $7.
Okay, so one number apart per 2 plus 2 plus 2.
Which is just 1, so the slope is 1.
Nice. Okay, we've got inclination, calculating slope from points. How does slope help us compare different lines? Like, are they parallel or perpendicular?
Slope is absolutely key for that. It's really straightforward for parallel lines. 2 lines are parallel if and only if.
They have the exact same slope.
The exact same slope. $1 is M22. Makes sense, right? Same steepness, same direction. They'll never meet.
That's pretty intuitive. What about perpendicular lines, the ones that meet at a perfect right angle, 90 degrees?
That also has a clear rule with slopes. 2 lines are perpendicular if and only if the product of their slopes is -1.
Product is -1, so $1 times meter thirds equals -1.
That's the condition.
Right.
$2 2 dot meter 2 exclase -1. Another way people think of it is that one slope is the negative reciprocal of the other.
Negative reciprocal, like flip the fraction and change the sign.
Exactly. So if one line has a slope of, say, 2, which is like frax 2 1 mol.
The perpendicular line slope would be frac 2 per.
Perfect. $2 times $1 1 works. Or if a slope is frac 3 or.
Flip it to frac 2, then negate it. So positive frac 3.
You got it. Check for times frac 4 3. That's the relationship for perpendicular lines.
What about our special cases, the horizontal and vertical lines?
Good question. Horizontal lines have slope 0. Vertical lines have undefined slope.
So, you can't multiply 0 by undefined to get -1.
Right. The $M natus metal really applies when both lines have defined non-zero slopes. We just know by definition that horizontal slope 0 and vertical undefined slope are perpendicular.
Makes sense. And the source material showed using the parallel rule, didn't it, with finding a missing coordinate?
Yeah, that was a good one. The line joining A, 3, 3, 4, and B, $2, and H is $1, is parallel to the line joining C, Lennis is 2 level, and D, $2, X dollars.
Okay, so first find the slope of AB. MAB, frac 1 seer did x1, dollars 1.
Right. Now find the slope of CD in terms of X minus 10 next to lever for RO1.
And since they're parallel, these slopes must be equal. So $1 frac x plus $2.
Multiply both sides by -1. $1, X plus 2.
So $6 must be $1 2 minus $1.
And that's how you use the parallel slope condition. $6.
Clever. Okay, parallel, perpendicular. What about 3 points? When do they all fall on the exact same straight line? Collinearity, right? Collinearity, exactly. And yes, slope tells us this too.
Let me guess. If 3 points A, B, and C are on the same line, the slope between A and B must be the same as the slope between B and C?
You nailed it. That's the condition. Slope of AB must equal slope of BC. If the steepness is the same between consecutive pairs, they must all be lying on the same line.
Okay, and the example was A, 2, 3, B, lana $5, and C, lana $5. Find A if they're collinear.
Right. So first, slope of AB, line of 5, 2, bus stand of 5, 2.
Okay, slope is fra 3. Now slope would be c, fran for f2 plus 5 times fra 3.
And for collinearity, these must be equal. So fra for 3, to solve for a, cross multiply. $3 times 3 is 7 times a, so $9.782.
Meaning a fraffata fraction, but that's the value that makes c lie on the same line as a and b.
Wow, slope is pretty powerful. Okay, shifting gears slightly. Intercepts, where the line hits the axis.
Yeah, intercepts are important landmarks for a line. The x-intercept is simply where the line crosses the x-axis.
And that always happens when the y-coordinate is 0, right?
Always. The point will look like A, where A is the x-intercept value. It tells you how far along the horizontal axis the crossing point is.
And similarly for the y-intercept, where it crosses the y-axis.
Yep. That's always where $6. So the point is EAT, and B is the y-intercept value. It tells you the height where the line crosses the vertical axis.
Okay, that seems clear. Now, we've talked a lot about lines, properties, points, slopes, intercepts. How do we actually write down the equation for a specific line? The sources mention several different ways, different forms.
Yes, absolutely. There isn't just one way to write the equation, and different forms are useful in different situations, depending on what you know about the line. My most famous is the slope-intercept form.
Ah, phi equals mx plus c.
That's the one. Y equals mx plus c. Super useful because it directly tells you the slope and the y-intercept.
So if you know those two things, you can just write the equation down immediately.
Instantly. Like the example, inclination $45 means slope m a Gilbert sign, and if the y-intercept is 5, so 3 poles $5, the equation is just phi equals 1x plus 5 phi, or I equals x plus 5 phi.
Simple enough? What is the next one? Point slope form?
Point slope form, yes. That's y1x by 1.
Okay, what are among by 1, y1 here?
Y is still the slope, and 6 by y1 is any specific point that you know is on the line.
Oh, I see. So you need the slope and just one point on the line, not necessarily the y-intercept.
Exactly. Very handy if, say, the rate of change slope and one data point.
Right.
Like the example, inclination $60.
So the slope 1 hour descent 60 stirp, which is quartile.
Right, scored a line, and it passes through the point amidst to $5. So $6 and over 3, $y by $5.
Plugging into the form, y vi will score 3 x noodles all 3.
Which simplifies slightly to y equals 3x plus $2. That's the equation in point slope form.
Okay. And what if you don't know the slope to begin with, but you just have 2 points?
Then you use the, logically named 2 points form.
Let me guess. You use the 2 points to find the slope first.
Basically, yeah. The form looks like this. Frax y, y1, x2 by 1.
Ah, okay. The fraction part. Frax y1, f2, that's just the slope formula we already talked about.
Exactly. So you calculate the slope using the 2 points tech by 1 and left by 1, and then you essentially plug that slope and one of the points into the point slope form.
So the example line passes through 1 along water and $1.
First, find the slope. 1 along fract 1, 1, 1, 1.
Okay, slope is 1. Now use 1 point, say 1 all and the slope in the point slope form. $1 is 1x, 9 is 3.
Which simplifies to your $1 is x plus 3, or just 1 lanos x plus 4, 3.
And if we'd use the other point, 1 all 3, would we get the same thing?
Let's check. 1 walls, 1 by 1. That's y phi $1 by $1. Add 5 to both sides. 1 more dollar in plus 4, 3.
Same equation. Nice.
It has to be the same line, so the equation has to simplify to the same form.
Okay. The source is also mentioned using the intercepts themselves to find the equation.
Right. If you know the x-intercept is A and the y-intercept is B.
That means the line goes through the points A and $2 B, doesn't it?
Precisely. So now you have 2 points. You could just use the 2 points form we just discussed.
Or calculate the slope from A and $2 and AGOB, slope on a for fra B and G0AA.
Yep. And since you know the y-intercept is by $1, you can jump straight to the slope-intercept form. A and 0x plus B.
Example, x-intercept 8, y-intercept manage 12. So points are $8, $8.
8 is 8, frac 3.
And the y-intercept is 2 sealers and these is 12, 2. So slope-intercept form is y frac 3 down 2.
Perfect. Or you could write it as 2a dy is 3 by 24 fluorosh, just clearing the fraction.
Yeah.
Still represents the same line.
We also saw examples working kind of backwards, like given the slope and just one of the intercepts.
Yeah, that's straightforward too. If you have slope dollar and x-intercept, you know the slope of the dollars in a point cell. A point slope form works great. Y dollar is made as a x,
which is just y mxa. Example, slope 3, x-intercept negative 3, point is $3.
So y dollars lures right 8 or a $2 is 3x.
Which multiplies out to d x plus $9 plus 901.
Exactly. Or if you have slope dollars and y-intercept sick, well, that's just the as plus co direct.
And one more case. Given a point and the y-intercept.
Okay, so you have a point by 1 Waller and the y-intercept CR, which means you also have the point dollars.
Ah, so now you have 2 points again. You can find the slope between them.
Exactly. Example, Breichel passes through $2, the y-intercept is 3, So $0.2, $3.
Or $2, $3, 3, 2.
And we know $2 extra. So the equation is y plus 2x plus 3 at 3.
Makes sense. You figure out the slope and use the piece,
Well said.
point or intercept to get the full equation.
That's the process. And finally, the sources showed how to go the other way. Start with an equation like 3 by 4y plus 12 and find the intercepts from it.
Right. For the x-intercept, we set $y.
Yep. Set y dollars, you get 3 by $4 plus 12y plus 12 plus $12 too.
Which means $3 expanded to 12 too, so 6x is going to 4 free. That's the x-intercept. The point is $4.
Correct. And for the y-intercept, set $3.
4y plus 12 plus 12 plus 12, $2. Divided by minus 4 by y is 3. That's the y-intercept.
Yeah.
That's the y-intercept, 0.2, $3. And the source even calculated the distance between those two intercept points, $24, 3 or $3, using the distance formula.
Right. Square root of $3, 2 plus 32 plus 16 plus 9 plus 9 on a 5. Just another property you can find once you have the intercepts.
It really feels like it all connects the equation, the graph, the slope, the points, the intercepts.
It absolutely does. Being able to move between the algebra and the visual picture and understanding what each part of the equation tells you about the line's properties, that's really the core of understanding linear relationships.
Okay, let's try and wrap this up then. Let's summarize the key takeaways. We've really seen how these linear equations are basically a mathematical description for a straight line on a graph.
Yeah, one-to-one mapping. And concepts like inclination and slope, they give us precise numbers for the line's direction and how steep it is.
And we learned those crucial rules for slopes. Equal slopes mean parallel lines.
And slopes multiplying to -1 mean perpendicular lines. Very useful.
Plus the condition for collinearity checking if the slope is consistent between points to see if they line up.
Right. And finally, we looked at all those different ways to write the equation. Slope-intercept, point-slope, 2-point.
Each useful depending on what information you start with.
Exactly. Mastering these gives you a really solid foundation, a toolkit for analyzing anything involving straight-line relationships. You can now confidently figure out how lines relate, check points, describe the lines mathematically.
So for you, our listener, here's something to maybe chew on. These ideas, they seem simple, right? Lines, slopes.
Yeah.
But they are genuinely the bedrock for a huge amount of more advanced math and, maybe more importantly, tons of real-world applications.
Definitely. Think about how just representing a relationship visually as a line can make it so much easier to understand, maybe even predict things.
Yeah, like in physics tracking motion, or engineering looking at forces, or even economics and data science looking at trends on graphs. Lines are everywhere.
They really are. So the thought to leave you with is, what other kinds of shapes or relationships out there can be described using mathematical equations? And how might you analyze their properties, maybe using similar ideas to what we discussed today with lines looking for key features, rates of change, points of interest?
It's a really fascinating path to think down. How math gives us the tools to describe and understand the world in these structured ways. Anyway, that's our deep dive for today. Thanks for joining us.